So for this problem here, okay, our givens are as follows. We have a ball that's initially traveling at 25 meters per second. So they're giving us VI, 25 meters per second. It hits a sand trap and slows down with an acceleration of negative 20 meters per second squared. Now, that's the way that this book would write things. I would not write them that way. I'd give you either slows down or negative, but not both. Because as we all know, 2 wrongs don't make a right, but 3 do. Keep that in mind for life lesson. Okay. So we've got our acceleration being negative because it's backwards. It's slowing down. Okay, but I would either, like I say, I would either say slows down at 20 meters per second squared, or I would say has an acceleration of negative 20. But I wouldn't say both because I find it's confusing. Okay, when you read it. All right, so our acceleration is negative 20 meters per second squared. Okay, we're looking for its displacement after 2.0 seconds. Okay, so from our list of formulas that we got the other day, and I still haven't given you guys a formula sheet, have I? I will do that today. Okay, we only have one formula that contains these 4 things, and it's this one. D equals VI times T plus 1/2 AT squared. Okay. Now, this formula is also derived from a velocity versus time graph. Alright, so if I've got a velocity versus time graph that looks like this, I have an accelerating object. Okay, that accelerating object, okay, I can calculate the displacement of it as long as I calculate the area under the line for this graph, which is basically just taking the average velocity and multiplying by time. Now, what that means is there are 2 shapes, the rectangle and the triangle. Are you with me so far? Okay, so average velocity times time gives me the areas of these 2 shapes. Well, for this box, okay, the average velocity doesn't change, but it also happens to be the initial velocity. So this box here is equal to VI times T. Right? The base, T, times the height, VI. Right? This top box, we take average velocity and multiply by time, which is actually the same as taking half the acceleration and multiplying by T squared. So that calculates that triangle, and now we've calculated the area under the line from a velocity versus time graph. Okay, gives us our displacement. So that's where that formula comes from. Okay. Now, in this case, I don't need to manipulate that formula. I'm looking for D, and I have all the other stuff. All right, so if we're going to fill this one in, then we're going to have D equals 25, our initial velocity, okay, times 2 seconds, plus 1/2 times negative 20. And this is where people run into trouble with this formula. They oftentimes forget to put negatives in it, okay, when they're appropriate. Okay, in this case, it's appropriate. Okay, times T squared, so 2 squared. All right, so we got 50. So put it all in here. So 25 times 2 plus 1/2 times negative 20, okay, times 4, 2 squared. All right, so the displacement of this golf ball is going to be 10 meters in a forward direction. Everybody okay with that? Okay, let's look at the manipulations of this formula, because this formula can be tricky. And in fact, there's one manipulation you're never going to be asked to do. Right? So we've got D equals VI times T plus 1/2 AT squared. Okay, let's say I want to solve for VI. What do I move first if I'm looking for VI? Exactly, I subtract the whole second half of the equation over to the other side. So I'm going to have D minus 1/2 AT squared. That makes sense, right? This is the total displacement, or the area under the line, minus the area of the triangle equals the area of the rectangle. Am I right with that? Okay, I'm trying to get VI. What do I do with T? Divide it. Okay, now here's a mistake people make. Does that cancel with that one? It does not. Okay, there's an addition subtraction operation on the top. I do not cancel anything. Okay, but I have people who do that because they see a T on the top, T on the bottom, and they automatically go into math mode. They're like, oh, I can cancel those. No, you can't. Okay, I can cancel those if everything on the top is being multiplied, then I can. Okay, but not in this situation. All right, so that'll give me my manipulation for VI. All right, what if I want to solve for A? What should I move first? Right, subtract the VIT over to the other side. So I'll have D minus VIT, so my displacement minus the rectangle equals the triangle. Right, I want to get A by itself, so how do I get the half and the T squared over to the other side? Just divide them, yeah. Okay, again, those T's don't cancel. Okay, we've got addition and subtraction operations there, so we can't do that. All right, that solves for A. All right, here's the tricky one. Solving for T. T's in two places in this equation. Okay, how many of you have done Math 20 already? Okay, that's a good portion of you. All right, we can't always guarantee that you've taken Math 20 before you've taken Physics 20. The only way to solve for T here would involve factoring. We can't guarantee that you've done that yet, and they don't require me to teach it, lucky me. So you won't be asked to solve for T using this formula unless VI is 0. How does that make it easier? Yeah. If VI is 0, D equals 1/2 AT squared. I don't have to worry about the other T. Now I can solve for T. Okay, it's an easy manipulation. I just divide both sides by half of A and square root, and I've got T. But you won't be asked to solve for T if VI is not 0. Okay, because it would involve you having to factor the equation. Okay. All right. Questions on how that one works? Okay. Then I would like you to try these two. They both involve using that formula. Okay. Watch out for kilometers per hour and minutes. Okay. You gotta make sure all of our units match. So make sure your units match. Okay, so for number 1, okay, we've got a skier moving down a uniform slope at 3 meters per second. So they gave us VI, 3.0 meters per second, and that's downhill. Okay, the acceleration is also down the hill at 4 meters per second squared. Okay. Find the skier's displacement, so we're looking for D after 5 seconds. Okay, so we don't have to manipulate, it's already set up to solve for D. VI times T plus 1/2 AT squared is the formula we've got to use, so that'll be 3 times 5 plus 1/2 times 4 times 5 squared. Okay, and when we do that, we should get 65 meters, and their answer is wrong. Why is their answer wrong? Why is down wrong? They never say down in the question. They say down a slope and down a hill. Down a hill and down a slope are different than down. I know that seems really picky, but it's also true. Down would imply the skier fell through the mountain because down is straight down. And this skier is not going straight down. They didn't fall off a cliff. Okay? They were skiing down a slope. Downhill is the correct vector for that question. And I know that seems like super anal, but it's true. Okay? Downhill is different than down. It just is. All right, how many people have done number 2? Okay, I'll give you a few more minutes on number 2. Remember that the conversion factor for kilometers per hour to meters per second is to divide by 3.6. Okay. Okay, so let's look at number 2 here. So we have a motorcycle traveling at 100 kilometers per hour. Okay, we need that initial velocity to be in meters per second. So we take that 100 kilometers per hour and we divide it by 3.6. It's going to be like 27.7. Okay, repeating. So we want to keep all those decimals. Okay, meters per second. Okay, on a flat road, it applies the brakes at 0.80 meters per second squared. What direction is that acceleration? Backwards. That's the key to this question. Okay? You won't get the answer right if you don't realize that brakes make you go slower, not faster. If you put in a positive for 0.8, you're going to say that slamming on the brakes causes the exact opposite effect that you desire, which is to slow you down. Okay? So, negative 0.8 meters per second squared, okay, for 1 minute. So our time is 60 seconds. All right, we're looking for D. How far did it travel in that time? Now, it asks for how far. Do I need to include a vector on my answer for this one? No. Okay. Yes, the acceleration has a vector on it, but the question only wants to know how far did it travel. And in this case, the displacement and the distance traveled are actually the same number because it's in a straight line. Okay, so I don't need a vector on my answer here, which is why they don't have one on their answer here on the board. Okay, so we've got D equals VI times T plus 1/2 AT squared. Again, I don't have to manipulate, I just have to plug in the numbers. So we'll have our 27.7 times 60 plus 1/2 times negative 0.8 times 60 squared, and that'll give us our 2.3 times 10 to the 2 meters. So it'll travel 230 meters before coming to a stop. Okay, questions on that one? Okay, I'm going to have you copy this one down. Okay, we've got to go over this. We got 2 more formulas, this one and 1 more, okay, that we got to cover today before we start kind of practicing these ourselves. All right, so for our speedboat question here, we've got that the speedboat slows down at a rate of 5 meters per second squared. So that acceleration needs to be negative. Okay, and comes to a stop. What's VF? 0. Okay, the process takes 15 seconds. Okay, find the displacement of the boat. All right, so I've got A, VF, T, and I'm looking for D. All right, other acceleration formula, okay, is this one. D equals VF times T minus 1/2 AT squared. So it looks a lot like the one we just used, but it's kind of the evil twin, okay, of the other one. Okay? It finds the same thing, but it does it from a different perspective. Right? The first formula we talked about, we said it calculated the area under the line to calculate the displacement. So does this one. It just does it differently. Instead of finding the rectangle and adding it to the triangle, what it does is it takes the final velocity, multiplies it by time, and finds this whole square. And then it subtracts this triangle because that triangle and this triangle are the same. All right, if I draw a box, okay, using the edges of the corners of the triangle to make it, I'm going to make 2 identical triangles. They'll just be mirror images of each other. Everybody all right with that? Okay, so all this formula is doing is finding the big box and subtracting this triangle here, okay, in order to get the area under the line. All right, so it's just doing it from the perspective of starting from the end and going backwards as opposed to starting from the beginning and moving forwards. Okay, so for this formula then, okay, we're being asked to find D, so that's good. We don't actually have to manipulate it. We're just looking to plug in our numbers. So 0 times 15 seconds. Do I even need to write that if I'm doing this? No, because 0 times anything is 0. Okay, on this one, I do have a tendency to write it, however, because I need to remember that I'm subtracting something from that 0. Okay, in other words, I have to be careful about my signs and whether I get positives and negatives and stuff like that. So minus 1/2 times negative 5 meters per second times 15 seconds, and that's squared. All right, so when I punch this into my calculator, okay, I'm not going to bother doing 0 times 15. I'm just going to go 0 minus, okay, 0.5 times negative 5 times 15 squared. I could have also just gone negative 0.5 times 5, that way. All right, so I'm getting 562.5 meters. I only have 2 significant digits in this question, so I would round this to 5.6 times 10 to the 2 meters. And it's forward. Or positive, they didn't really say. It just says it's slowed down. Okay, so I would say forward or positive or something like that as a direction. Okay. Everybody all right with that? Okay, manipulating rules, very similar to the other one. Okay, you're not going to be asked to find t unless VF is 0. Okay, and the rest of the manipulations are kind of the opposite. So we've got d equals VF times t minus 1/2 AT squared. So if I want to find VF, I add the 1/2 AT squared over to the other side. Okay, and then I divide both sides by t, and that'll leave me with VF. Okay, so very similar to the last formula for that one. All right, if I'm looking for A, then I would subtract, actually in this case I would add the 1/2 AT squared over here, so it becomes positive is usually what I do. So I'm going to have d plus 1/2 AT squared equals VF times t. Then I subtract the d over, and then I divide off the 1/2 and the t squared. That way I know what I'm looking for is going to be positive and I don't mess something up. Okay. You all right with that? Okay, it's just algebra, right? You guys are good at that already. Okay. Questions on that formula there? Okay. Then try those 2 questions. They have to do with that formula. Okay, let's look at number 1 here. So number 1, we have the arresting device on an aircraft carrier. I don't know if you guys have ever seen like an aircraft land on an aircraft carrier, but aircraft carriers have a series of cables strung across the deck, okay, to recover aircraft. So an aircraft that lands on an aircraft carrier has to have a special hook built into the bottom of it. Okay? They usually release those just before they land. So it's just a hook that hangs down from the bottom that's attached to the frame of the aircraft. And when they land on the deck, the hook catches these cables. Now, it doesn't just yank it to a stop instantly because it would rip the aircraft apart and tear the cable and all that. So these cables are actually attached to a kind of a, it's not really a bungee system, but it's like that. Okay, it's a mechanical system that provides increasing resistance. So when they hit the cable pulls on these essentially braked wheels that are under the deck, okay, that slow the plane to a stop very fast. Okay, like it's not a pleasant landing. Okay, like landing in a passenger aircraft on a mile-long runway. Okay, they have to stop these planes. It says 150 meters on here. It's less than that. Okay, aircraft carriers are big, but when it comes to like landing a plane on them, they're quite short. Okay, so they're going to jerk this thing to a stop at negative 15 meters per second. That's more than gravity. Okay, to give you an idea, that's about 1.5 times the force of gravity. That means that when you hit the deck and catch that cable, the force that you would feel against your chest, okay, from the seatbelt in the aircraft would be equivalent to 1.5 times your weight. So taking somebody 1.5 times as heavy as you and having them stand on your chest. Okay, that's how much force you would feel, okay, when your plane gets stopped on the deck. Right? It's why guys that are like fighter aircraft pilots have giant necks. Okay, they have incredibly muscular necks because if they didn't, their heads would fly off. Okay, because they wear like a big heavy helmet on top of their head, and when you get jerked to a stop, okay, by one of these things, it's a lot of force, okay, on your spine and chest and stuff like that. Okay, so we've got our numbers here. We've got a displacement of 150 meters. That's positive. The aircraft still moves forward while slowing down. Okay? The acceleration is negative 15 meters per second squared, and it comes to a stop, which means VF is 0 meters per second. We're looking for the time. And I said I'd never ask you to use this formula to solve for time unless VF is 0, and it is in this case. So D equals VF times T minus 1/2 AT squared. All right, so what I'm going to do is start out with this. I'm just going to go 0 minus 1/2 AT squared. Okay, make my life easy. Now, do I need to keep the 0 there? No. I just need to keep the negative there. Right? Now I can manipulate the equation. So I'm trying to solve for t, so I'm going to divide both sides by negative 1/2 times a. And then I'm going to square root. Now, here's where signage is important. If I do not put the negative sign on my acceleration, my calculator will have a fit. Because it'll tell me I'm trying to do something impossible. Like taking the square root of a negative number. Okay? I can't do that. Right? So I have to make sure I get my signs correct. If your calculator says that you're crazy, you probably just forgot, okay, a negative sign somewhere. Okay, so what we have for this question then is is 150 divided by negative 1/2 times negative 15. Okay, that'll take care of it. There'll be positives top and bottom, and I can take the square root of that number, and I'll get 4.5 seconds. Okay, for my answer. And I'll just show you what that looks like on the calculator. Okay, so square root of, in brackets, 150 divided by, in brackets, negative 0.5 times negative 15. So we get 4.5 seconds positive. Okay, everybody all right with that one? How many people have done the second one? Okay, I'll give you a little bit more time then on the second one. This one. All right, so the 1968 Corvette took 6.2 seconds to accelerate, so they gave us the time, 6.2 seconds, to accelerate to 160 kilometers per hour north. For whatever reason they put north on there, okay? But we've got a direction now. So 160 kilometers per hour, we've got to convert that to meters per second. Okay, it's actually 100 miles an hour, okay? Divided by 3.6. So we're looking at 44.4 repeating. So VF is 44.4 meters per second, okay? And it travels 220 meters in that time. Okay, we're looking for the acceleration. All right, so we've got D equals VF times T minus 1/2 AT squared. All right, trying to solve for A. So what I'm going to do is bring the 1/2 AT squared over to the other side so I get rid of the negative. So I'm going to have D plus 1/2 AT squared equals VF. You don't have to do it this way, okay? You could just move the VF times T over, but then you have to remember you still have a negative hanging around that you have to account for. Okay. Now I'm gonna times D. Okay. I'm gonna subtract the D over, so minus D, and then I'm gonna divide by 1/2 of T squared. All right. So that's gonna solve for A. Okay. That's my manipulation there. So we've got. We got 44.4 times 6.2 seconds. Okay, minus the displacement, 220 meters. Okay, and then divide that by 1/2 times 6.2 squared. That'll leave me with my acceleration. So when I'm plugging all that in, so I'll take that and multiply by 6.2. Okay, subtract 220, and then divide that by 0.5 times 6.2 squared. All right, so I'm getting an acceleration there of 2.9 meters per second squared north, okay, which is also the thing. Okay, making sense? So there's a lot of algebra in acceleration because you got a lot of formulas that you have to move stuff around it. Okay, the big thing for acceleration is looking at your givens and deciding which of the formulas you have, and you have 5 of them, okay, that you should use. All right, we got one more acceleration formula. So we'll look at this problem here. I'll have you guys copy that one down, right? And then we'll talk about it, and then we'll talk about some applications of this stuff before we work on something. So our givens for this question are, okay, we've got a bullet that accelerates the length of the barrel of a gun, which is 0.750 meters. So that's our displacement, or distance actually in this one. Okay, 0.750 meters. Okay, with a magnitude of 5.35 times 10 to the 5 meters per second squared. Is that a lot? Yeah. Yes. Okay, but I mean that's how guns work. The explosion of the gunpowder produces rapidly expanding gases that are essentially trapped between the bullet and the barrel. Okay, those gases need to go somewhere, so they push the bullet down the barrel, okay, and impart a great deal of velocity to it before it leaves the barrel. The longer the barrel, okay, the more accurate and the faster the muzzle speed, that's the speed the bullet leaves the gun at, okay, will be, because the greater the distance the expanding gases have to work on the bullet itself. Okay, does everyone kind of follow me on that? Okay, that's why handguns, okay, really are not good over long distances. Okay, they only have a short distance over which to impart force and do work and accelerate the bullet. So the muzzle speed of a handgun is much smaller than the muzzle speed of a rifle. Okay, they're also going to be a lot less accurate because once they leave the barrel, lots of things can act on them, and they don't get the spinning action that's produced by a properly rifled barrel. Okay, I don't know if you guys have seen like many of the CSI shows, but they usually do some sort of animation when somebody pulls the trigger of the bullet going down the barrel, and you can see these like grooves that have essentially been cut in the barrel. Okay, that's also how they can tell whether a bullet has been fired from a particular gun. Okay, because the rifling of the barrel is unique, and it will leave certain marks on the bullet itself. If they can recover it and it's not too badly damaged, they can determine that yes, in fact, that bullet was fired from that gun because of the pattern of rifling that it produced. Okay, so all of that stuff results in the speed that's imparted to the bullet. And the more the bullet spins, the more accurate it will be, okay? Because the spinning action actually helps to reduce how much it gets pushed from side to side as it flies. All right, so we've got D, we've got A, right? What else can we assume? Like, if the gun is being held and the trigger hasn't been pulled, how fast is the bullet going? 0. So we have to assume here that VI is going to be 0 meters per second. Okay, we are looking for the speed the bullet will exit the barrel at. All right, so we got VF squared equals VI squared plus 2AD. That's the formula we're going to have to use here, because it's the only one that has everything I've got for givens. Okay, could I solve this in 2 steps? Yep, I could. But why would I solve it in 2 steps when I can solve it in 1 with this formula here? All right, it's already set up to solve for VF squared, so the only manipulation I need to do is to square root the entire thing. And since VI is 0, I can just do that, and it's really just the square root of 2AD for this particular problem. All right, so I've got 2 times the 5.35 times 10 to the 5 meters per second squared for the acceleration, okay, times 0.750. All right, so this bullet is going to leave the barrel of this gun moving at 895 meters per second. Is that fast?
Yeah.
Yes. Okay. In fact, it is nearly 3 times the speed of sound. does that mean for you if the bullet is fired at you?
You're going to get hit before you hear it.
Right. There's a saying in the Army, you never hear the bullet. Right? Which isn't really true. You would hear the bullet right before probably, when it was that close to you, you could probably hear it whistling, okay? But you wouldn't hear the shot because the bullet's moving faster than the explosion that propelled it. Okay? I don't know if you guys have ever seen this, but they sometimes have shown footage of people in the military fighting insurrectionists in places like Afghanistan and places like that where military operations are going on. And you'll often see, okay, they'll have like a sniper or somebody set up to take out these people as they walk. And when the sniper fires, if they miss, what you see is not people turning to look for the shooter, but turning and looking down because the bullet hits the ground near their feet, and that's the sound they hear. So they look down, and then they do this, because then the sound gets to them, right? Then they're looking for where the shot came from. Okay? So, yeah, it can be a bit, I would imagine, disconcerting, right? Especially if you were one of the people that was hit by the longest sniper shot, which is nearly 4 kilometers. Canadian, too. Canadian sniper. Longest kill shot, Canadian sniper. Okay. Now, if you can imagine, 4 kilometers away, like you look out this window, okay, and 4 kilometers away is like past Darcy Ranch from here. Okay, that's a long way, okay, for somebody to make a shot from. Okay, so don't be on that person's bad side would be my advice. Okay.
Find someone from that far away.
Well, snipers never work by themselves. That whole idea that snipers are these lone wolves is really not true. They usually have a spotter. So the spotter's got a telescope, well, not a big one, but one that they're using. They know people are coming to them because they've got intelligence telling them that they're in an elevated position so they can see them from a long way away, right? Yeah, for us, there's hills and stuff like that between us and there. So yeah, you have to be in the right place, you have to have all the right conditions, right, to make a shot like that. Okay? And for a shot of that distance, you've got to consider things like how far the bullet will drop. When we talk about projectile motion, we'll talk about that. A bullet doesn't fly in a straight line, right? It arcs down towards the ground because gravity pulls it. So a person who's shooting a shot that far has to account for how far the bullet will fall while it's flying to target. Okay? That can be several seconds for a shot that long. Bullet can fall over 20 meters, meaning you have to aim over 20 meters above your target. Okay? They also have to take into account wind, okay, that's going across the shot, and to an extent, the Coriolis effect. That is the rotation of the earth under the bullet while it flies. Okay? Any shot over a second in flight time, you need to account for the fact the earth will rotate under the bullet. Crazy. Don't get on that person's bad side. They can take all of that into account and hit that shot. You want to be their friend, not their enemy. Okay? For sure. Okay, that one making sense? We use this formula a lot in projectile motion. Okay, because it doesn't require us to know the time. Okay, I want you guys to try these two. The first one actually doesn't require you to use the formula we just used. And you can for part of it, but you won't use it for the first part. You'll have to figure out which formula you want to use for that one. Okay, so on number 1, our initial givens are VI, 70 meters per second, okay, VF being 0 meters per second, and the time, 29 seconds. Okay, so they want to know what the jet's acceleration is. So I'm not using VF squared equals VI squared plus 2AD because I don't have D, right? I have time instead. So what formula should I use to calculate the acceleration here? Right, our good old Science 10 formula. A equals VF minus VI over T. That'll get us the acceleration for part A. Okay, so we'll have our 0 minus 29, sorry, not 20, minus 70 over 29. Okay, so we got negative 70 divided by 29 seconds gives us an acceleration of negative 2.4 meters per second squared. Okay, so now we've got that. For part B, it asks, what length of runway did the jet require to come safely to a complete stop? I now have VI, VF, T, and A. Can I use any formula I want to calculate D? Except the one I just used. I can't use that one, because obviously it doesn't have D in it. Okay? But I can use any of the other formulas that I want, and they would all be correct. I would say using this one is probably the one you wouldn't want to use. Okay? I would say that's probably not your best bet. Okay? I wouldn't use that one here. Not to say you couldn't, okay? But I would go with something else that maybe is already set up to solve for D, like VI times T plus 1/2 AT squared. Right? I don't even have to manipulate that one. It's already set up to solve for D, and I would just plug in my numbers. So I'd have 70 times 29 plus 1/2 times negative 2.4, okay, times 29. Right? And I would keep that rounded value for part B. Okay? If I calculate something in part A and I use that value in part B, I use the rounded value in part B. All right, so when we do that, we got 70 times 29 plus 0.5 times negative 2.4 times 29. All right, so this thing is going to travel almost 2 kilometers before coming to a stop, okay? I think we only have 2 significant digits here, so it is actually going to be 2 kilometers. I don't know why they have 1 kilometer there. Did I put something in wrong? I probably did. I didn't square the 29. That's exactly it. Okay, so yeah, 1.0. Into the 3 meters, or 1 kilometer, okay, would be our answer for that one. Okay, how many people have done number 2? Okay, I'll give you a couple more minutes to finish up number 2, and then we'll go over that one. Okay, we were on that topic of longest sniper shots. I just looked it up. 3 of the top 5 are Canadians. All 3 different Canadians, too, not the same guy. 3,540 meters is the longest one, so 3.5, more than 3.5 kilometers. Okay, so looking at number 2 here. Okay, so we got on-ramps, okay, designed to get you up to highway speed before you enter the highway. At least that's what they're designed for. not everybody realizes that. If you've ever tried to, get onto Deerfoot just over here from that exit ramp, like, there's some people that just don't get that you depress the pedal on the right to go faster, okay? And they like slowly try to come up to speed. Meanwhile, you're trying to merge, but they're going 60. Everybody else is flying by at 120. So in case you didn't know, that is for going faster that lane, okay? Get up to highway speed quick. All right, so we got a car that is moving or is increasing its speed from 50 to 100 kilometers per hour. So the first thing we need to do is put those into meters per second. Okay, so we know this one's going to be 27.7 already because we've had 100 kilometers per hour before. Okay, so this will be half of that. Okay, we might as well just get both of them here. So 50 divided by 3.6 is giving us our 13.8 repeating. Okay, and just so we have the number in our calculator, 100 divided by 3.6. And now we got them both. Okay, so we've got that, and we are looking for a acceleration here of 3.8 meters per second squared. All right, so this is the kind of calculation that a city planner would need to do if they were planning on building a highway interchange. Okay, like they did there with all of Stony. Okay, for the last few years they've been building all those interchanges. So when they're designing those, they need to know, okay, what's the speed limit on Stony Trail? Okay, how much, people are going to be going this fast on the ramp. They need to get up to this fast. How long does the ramp need to be? So I put the ramp in the right place and make it merge onto the road. Otherwise, they could have it just go straight onto the road, and there's going to be tons of accidents because people don't have enough room to accelerate, or they make it way too long and they waste resources. Okay, they don't need to make it that long. Cars could have easily gotten up to highway speed before that. Okay, so they have to take that kind of stuff into account. So we're looking for D here, and I would say this is the formula that we want to use. VF squared equals VI squared plus 2AD. Okay, looking for D here, so the first thing I would do is subtract VI squared over to the other side, and then divide both sides by 2A. That'll give me D. Okay. What do you suppose the most common mistake is when using this formula? Yeah, just like I did on the last question. They forget the square. Okay, they forget to punch the square in. So we've got here our 27.7 squared minus 13.8 squared divided by 2 times 3.8. So when we're punching that in here, we're going to have our answer squared minus that number squared and divided by 2 times 3.8. Okay. Seems long. Put something in wrong somewhere? I did. I must have put something in. I must have missed something, I guess. Oh, I know what I did. Oh, no, I put it in brackets. Weird. Anyone else seeing it? I'm not seeing it where I went wrong here. Anyway, try it again. I don't know what I did wrong the first time, but okay, getting 76 meters that way. I'm not sure what I did wrong there. Okay, I definitely entered something in the calculator wrong, but okay, we got 76 meters, okay, for the length of that ramp. Okay, everybody all right with that one, besides my screw, which I still can't figure out what to do about. Okay, all right, so we're going to be working on acceleration tomorrow. You will have a quiz tomorrow. Okay, I'll post it. Well, post the practice one later on today.
So just a question about the last question. Couldn't you just chosen the initial velocity instead of popping that answer back to use it with the final velocity?
Sorry, I'm not understanding what you're asking.
Like for getting the distance, couldn't you have just chosen the
Oh, I see what you mean. Could I have just said that the top was the initial velocity squared?
yeah. Wait.
No, I couldn't
No, never
have.
mind.
No, I couldn't
No,
have.
never mind. I got the average velocity. Never mind.
Okay.
Yes, sorry.
Yeah, so tomorrow we'll be working on acceleration. Okay, we'll have your quiz. I'll post it later. Wednesday we'll be looking at probably finishing that up and maybe starting an activity that day. Thursday we're doing a lab on acceleration. Okay, and Friday probably moving on to maybe projectile motion on Friday. So that's what's coming up here going forward. Now, before you back up, we're not done. I'm just letting you know what's going on. Okay, anybody watch the Perseverance rover land the other day? Okay, I didn't think anyone would have, but they're going to release the actual landing video taken by the craft itself today. Okay, you want an example of people having to use acceleration formulas? There it is. Okay, trying to land something on the surface of Mars from another planet is absolutely an example of the stuff that we've been going over. Okay, so if we've got, here's Mars. Okay, I should have drawn it in red, but I didn't. Okay, now you got a spacecraft that's coming towards that planet at an unbelievable rate of speed. Okay, even though it's got retro rockets that slow it down whenever, when it gets to the planet, it's going really, really fast. Okay, the only way you make sure that your rover doesn't become a smoking crater, like many of them have, okay, is that you have to brake it, and not like brake it. You have to use braking to make it slow down. Right? And you can either do that using retro rockets, which use a lot of fuel and are very heavy and would be difficult to launch into space from Earth, or you can use the atmosphere of the planet you're encountering. And that's what we do. We use Mars's atmosphere to slow down any landers that we're going to put on its surface. There's a bit of a problem with that. You can burn up if you do it wrong, or bounce off it if you do it wrong. Okay? It's a delicate balance. Okay? The other issue with Mars's atmosphere is it is 1/100th as thick as ours. Okay? So it doesn't provide nearly as much braking power as Earth's atmosphere does when we're trying to enter spacecraft from orbit. Okay, we're trying to bring them back to Earth. Earth's atmosphere is much thicker, so you can burn up a lot more easily, and it provides a lot more braking, a lot more friction. All right, so what has to happen is, as the craft approaches, okay, they have it encounter the atmosphere at a shallow angle. If the angle is too shallow, it's like skipping a rock off the water. And it will simply bounce off the atmosphere and out into space, and there'll be no way to recover it. Okay, it just doesn't have enough fuel to go, oh, well, we'll just turn around and try that again. Okay, that's not how things work for us. Okay, so what you have to do is make it hit the atmosphere and start slowing down. The first part is just a heat shield, a big ceramic construction that goes on the bottom of the spacecraft, okay, that is designed to be ablated, that is burned off. Right? So it'll encounter the atmosphere and start slowing down with this heat shield, okay, causing it to do this. So Mars would actually be like this much, and this would be the atmosphere. Okay, so you get this thing. It starts slowing down, and also starts arcing in because as it slows down, gravity's pulling it towards Mars. Okay, so you can do that for a little while, but eventually that heat shield is basically too hot to keep around. So you jettison the heat shield and you open up some parachutes. Okay, each one of these parts, though, the acceleration isn't uniform. It's not like what we've been doing, where the acceleration is this much and it stays that much the entire time. Okay, the further into the atmosphere you get, the more the acceleration changes. Okay, because the thicker the atmosphere becomes. Right, so you got to this point, then you jettison the heat shield and you open up these parachutes, these special supersonic parachutes. Okay, that are designed to slow down the spacecraft, okay, and so it'll start arcing in even more. Okay, then you get to a point where you actually jettison the first set of parachutes and you open up a second set in some cases. Okay, that makes the spacecraft drop even faster. Okay, and then at the very end, they've got this really novel thing that they used for the last two rovers called the sky crane. Okay? It is a ring of rocket engines with a winch in the middle. Okay? The rover sits in the middle of this ring, attached to the ring by these 3 cables. Okay? So this ring of rocket engines, okay, hovers right here with the rover underneath it. I can't draw very well, so you have to go with the buttons. Okay? So there's these rocket engines that are firing, and they're lowering the rover down towards the ground. There's a bit of an issue with that. Rockets will push debris up off the ground. Okay? These rovers are very tough, but also surprisingly delicate. And what you don't want is rocks propelled at high speed to be hitting them from the rockets. So, in order to prevent that from happening, the ring of rocket engines, called the sky crane, hovers and begins lowering the rover by cables until it's about 3 meters or so, something like that, off the ground. So now it's suspended by these cables, okay, that are just holding it there. When it's 3 meters off the ground, they cut the cables. Okay? Now I know you're thinking, holy crap, you dropped this like billion-dollar spacecraft 3 meters? That's like dropping it up halfway from the top of the gym. Okay? I wouldn't drop $1 billion from 3 meters. But remember, it's 3 meters on Mars. The acceleration due to gravity is 1/3 that of Earth. So it's only like dropping it 1 meter, okay, on Earth. So it can handle that. Okay? So it drops down, okay, and lands on the ground, okay, safely. And because the cables have been cut, now there's all this force and no weight. So the ring of rocket engines, the sky crane, just flies off and crashes somewhere. Okay? Nowhere near the rover, because that would be bad. Okay? We don't want to just lower it down to the ground and have these rocket engines spitting, well, flames and rocks and stuff everywhere all over this brand new shiny rover, okay? Because it would damage it, so they just cut it and it goes and crashes. Okay? So they're going to be releasing the footage. They didn't have footage of Curiosity when they landed it. Okay? This one they actually got footage of the whole thing. So they're going to release it today. You might want to watch it. It's pretty cool. It's called the 7 Minutes of Terror. Okay? Because there's another issue with landing something on Mars. Mars is really far away, and you can't land it or pilot it in real time, because it takes 13 minutes for your signal to be sent and returned to you. Okay, sometimes more than that, depending on where Earth and Mars are in the orbit. Okay, so you can't just go, all right, well, correct it here, correct it there, because it takes several minutes for that signal to get there. By then, your spacecraft is a smoking crater. Okay, in fact, when they're landing it, they're seeing footage, and the thing has already happened. Okay, what they're seeing has already happened several minutes ago. Okay, so it's very tough. It all has to be done by computer on the spacecraft itself. It has to land itself autonomously. It cannot be piloted from Earth. Okay, all right. Get everybody to clear off their desks, mask up. I'll come around and spray off your desks. You guys can wipe them down.